Hi there, welcome to the 10th episode of the filters tutorial. Today we will talk once more about the Sallen-Key topology widely used for second-order active filters. We will explore the high-pass filter configuration and we will see a simple method for calculating the parameters of the filter given its cutoff frequency and Q factor. Let's begin! Let's start with a quick refresh of the Sallen-Key filters. These active filters were invented by a couple of researchers at the MIT Lincoln Labs named R.P. Sallen and E.L. Key. The peculiarity of these filters is that although they use an op-amp in their schematic, the filter is almost independent on the performance of the op-amp itself, and that's because the op-amp is used only as an amplifier. In other words, the op-amp doesn't do either integration or differentiation of the signal, but only amplification, which in the base design of the filter has a gain of just 1. In its basic design, the Sallen-Key configuration uses an op-amp with a full negative feedback and two first-order filters, one made of Z1 and Z3, and the other, in series with the first one, made of Z2 and Z4. Depending on the nature of the four impedances, the filter can behave differently, like a low pass or a high pass, although keeping the same topology. The transfer function of this filter, based on the four impedances described in the schematic, can be written in this generalized way. Remember that the transfer function is just the ratio between the output and the input signals described in the S-domain, which keeps into account both the transient and the behavior of the circuit in the frequency domain. Let's now redraw the previous circuit, replacing the impedances with some specific components, like this. So we are basically replacing Z1 with a capacitor C1, Z2 with a capacitor C2, Z3 with a resistor R1, and Z4 with a resistor R2. Based on these substitutions, we can rewrite the transfer function by replacing the generic impedances with those that are specific for C1, C2, R1 and R2, which are respectively 1 over SC1, 1 over SC2, R1 itself, and R2 itself. This new transfer function can be readjusted to highlight its properties. First we readjust the denominator, then we multiply both numerator and denominator by s squared C1 C2 to remove the fractions at the denominator. And now we can define omega 0 as the inverse of the square root of R1, R2, C1 and C2. And so now we can rewrite the transfer function in this new form. At this point, we can replace the whole multiplier of the variable s at the denominator with 2 alpha, and rewrite the transfer function in a more familiar way. Now we can recall the definition of the Q factor, which determines the shape of the magnitude body diagram in proximity of the cutoff frequency. In particular, we can rewrite Q replacing the value of alpha. Divide by omega 0 both numerator and denominator, and finally replace omega 0 with its actual value in terms of R1, R2, C1 and C2. This is one of the two parameters that defines the way the filter works. The other parameter is the actual cutoff frequency, which we extract from omega 0. Now, given these two parameters, we can design the whole filter, which, if you noted, is a high-pass filter, given that the transfer function has two zeros at the frequency 0 and two poles. These are the only two formulas that you need to remember to design a second-order active high-pass filter with the Sallen-Key topology. To actually design a filter using the base approach defined by R.P. Sallen and E.L. Key, we proceed in the exact same way as the last time, when we designed a low-pass filter. Let's run an example on how to design the high-pass filter. First, we need to define the parameters of the filter, the cutoff frequency and the Q factor. Let's use, for example, a frequency of 10 kHz and a Q of 0.5. Now we need to define a generalized resistance and a generalized capacitance, and define our R1, R2, C1 and C2 as functions of this generalized value through the variables m and n. At this point, we use the generalized values of R and C to rewrite the equations for the Q factor and the cutoff frequency. Let's start from the Q factor. And as it happened with the low-pass filter, the Q factor only depends on m and n, and it is totally independent from R and C, which helps simplifying the calculations. Now we can arbitrarily define a value for one of the two variables m and n. Let's choose, for example, n equals 1. Based on this value and on the required value of the Q factor, we can find the value of m, which happens to be also a 1 in this example. Let's now work on the cutoff frequency. Because both m and n equals 1, the cutoff frequency can be rewritten simply as 1 over 2 pi RC, which we have defined as 10 kHz. And now, like we did with the m and n pair, let's arbitrarily define C as 10 nanofarad. Replacing such a value in the previous equation, we obtain that R must be equal to 1.6 kΩ to obtain the required cutoff frequency. And so, finally, we can calculate the actual values for R1, for R2, for C1, and for C2. And we can also draw the final schematic for our filter. And here is the schematic drawn in a more formal way. Note, however, that I have changed the resistors from 1.6 to 1.5K. I did that because I don't have the 1.K resistors available in my stock, and so I used the closest value I had available. The point is, using 1.5K instead of 1.6 will result in a slightly different cutoff frequency of 10.6 kHz instead of 10 kHz. If I needed to be precise, I had to buy some 1.6K resistors, but for the sake of the lab experiment we are close enough, and so I am going to leave it like that. Let's go now to the lab and test this circuit to see if it works as expected from the theory. And here is the circuit mounted on the breadboard. Here we have a UA741, which is a very simple pump. And then we have the two capacitors in series with the input, which comes from here. And then the two resistors, so one that goes across between pin 6, the output, and between the two capacitors, and then the other one that goes directly from pin 3 to ground. I have attached at the input the output coming from the function generator over here. You can see that it's currently set with a sine wave at 5 volts peak to peak and 34 kHz right now. And then we have the oscilloscope instead, which is connected to the output on pin 6. And here is the output wave on the oscilloscope. You can see it's a nice sine wave right now, and it's at 34 kHz. So let's now reduce the frequency, and we should see the level of this signal go down. By the way, let me adjust the cursors right now. Let me set it like this. Here we go. So this is going to be on the top. The difference here is 720 millivolts. Remember that there should be 707, but I cannot have that kind of fine-tuning with this oscilloscope, so we'll have to play a little bit to understand what's going on. Anyway, so this is the cursor. Now I'm going to decrease the frequency of the generator, and we should see a little bit at a time this sine wave shrink in amplitude. As soon as it reaches the lower cursor, then that will be the moment where we can read the cutoff frequency. So let's go down right now, slowing down the frequency. And here we are at about 11 kHz. Of course, this is not a perfect measure, but it goes very well with the calculated value that we already made of about 10.6 kHz. The filter works perfectly, and we can see that if we decrease further the frequency, the signal goes down faster and faster. You see, it's almost disappeared now. So at 2 kHz, the signal is already very, very low. At this point, you should be able to design your own second-order active low-pass and also the high-pass filters using the Sallen-Key topology. These filters do not have stringent requirements for the op-amp used in their core, and therefore they are very useful in a number of applications, ranging from audio to high frequencies. Even if you decide not to follow all the calculations to calculate the transfer function of the filter, you should still be able to do your own design based only on the final formulas for F0 and Q presented in the last two videos, along with the procedural examples. In the next video of this series, we will talk some more about the Sallen-Key filters, and we will see their application and variations for bandpass and four-notch filters, and examples on how to design such filters. To avoid missing these videos, I would suggest you to subscribe to the channel and to click on the bell to activate the notifications if you haven't done so already. And while you wait for the new videos to come out, you can spend some time looking at older videos from this channel, and I'm sure you'll find many other electronics subjects that will catch your interest. See you soon in the next video, and as usual, happy experiments!